Good afternoon, ladies and gentlemen. Welcome to I²CNER seminar. So today we have a distinguished professor from Shanghai Jiao University, Professor Ruzhu Wang. So I briefly introduce him. So Professor Wang graduated from Shanghai Jiao University 1984 and 1987 for the bachelor and master degrees. And he got PhD from the same university in 1990. So, and he was appointed the associate professor in 1992 and promoted to the full professor in 1994. So his major research area is heat transfer and refrigeration and air conditioning systems, especially the adsorption, refrigeration, the heat pumps and solar energy systems, was any other related to the energy saving issues. So for instance, the green building system, energy systems. And Professor Wang has already published 260 papers, and his citation in total exceed over 5,000 times. So he's now the director of the Institute of the Refrigeration and Cryogenics at Shanghai Jiao University. So he received many awards from many associations, societies, and government or something. So today's his talk is title is Sorption Thermal Energy Storage Concept, Progress, and Prospects. So we would like to invite him. Thank you. Please start.
So, good afternoon, ladies and gentlemen. It's my great honor for this invitation by Professor Takasa and to come here, I²CNER, the very famous research organization, to deliver a speech. And this speech actually is based upon that in the last several years, I got a lot of requirement, the demand from the user side, the companies. For example, they would say the uses of air source heat pump water heat in Japan normally is 300 liters. When it's possible, you change it to 100 liters, but the heat quantity will be the same. And also for Chinese customers, because the companies, if you use bigger tank for hot water, for example, normally you occupy some space. So they do need, if you have some chances to reduce the size and with a stable operation to contribute the heating supply, it will be a huge market. So this is actually the user side needed. So in this case, I want to say something based upon our original researches with a lot of research for sorption refrigeration. And it can be also used for sorption, thermal energy storage. And we will see whether this kind of new technologies could bring the effect to make thermal storage to be compact and efficient. So this is my main contents. And first I want to say something about introduction. And this introduction is actually, we say first for the thermal sorption refrigeration. So what we have, because this phenomenon comes from the requirement from the waste heat from industrial, or we have geothermal heat, or for transportation, for the engines, we have a lot of waste heat from the exhaust gases, or the jacket cooling for the internal combustion engine. And also now it's very warm for solar energy. So solar energy could supply you with 50 degrees to even 200 degrees centigrade. So whether you could use this kind of heat originally, we call it low-grade thermal energy. Originally, most of it cannot be used, and whether it's possible for the efficient uses for cooling and refrigeration. So this is actually what's the background of what we have done for the sorption refrigeration. And there are a lot of options for absorption, adsorption, or desiccant. And in Kyushu University, there are similar, a lot of researchers, very active research areas. And in the last several years, this was, I think, just this April, when we developed a new commercialized product for silicon gel water adsorption chillers. It uses hot water from 55 degrees to 85 degrees centigrade. And to get the cooling about 10 degrees chilled water for air conditioning with efficiency about COP about 0.4. So with this kind of system, now we are making more uses. This original, the small one, that was we developed in the year 2004. And now we make it into the modules, the module type. That means the design is very simple. So we could extend or make it reduced capacity very easily. So we made a heat exchangers adsorber into the standard modules in this case. And also we developed chemical reaction, this calcium chloride adsorption on ammonia. And in this case, you get the refrigeration effect to minus 10 degrees or minus 30 degrees centigrade. Normally we need about 120 to 140 degrees centigrade to drive this system. So this comes from the requirement from industry, specifically for the chemical industry. They do have a lot of waste heat at a temperature between 100 degrees to 200 degrees centigrade. So some waste heat could be upgraded for the use, and some cannot be used. But in the processing or industrial processing process, they do also need refrigeration. So in this case, there are several ways. You could use waste heat 100 degrees, 150 degrees to power by organic lumping cycle to get electricity. And then electricity to generate the power normal vapor compression refrigerant. But if you go this way, the efficiency is low. You could directly using the sorption process and to get a high efficiency for refrigeration or cooling. And also for the uses of solar energy, we developed so-called single or double effect switchable absorption chillers. So in the market, actually, for the lithium bromide water absorption chillers, normally it's double effect. And you need 140 degrees centigrade to generate. But for the solar cooling, actually, mostly just the daily time, if you try to get the temperature of solar collector more than 140 degrees centigrade, possibly you could guarantee using parabolic track or medium temperature solar collector, you could guarantee about 4 or 5 hours. And the other times, that's lower the temperature. In this case, you use single effect. So in this case, you could develop this concept to use single effect or double effect, depending on the heating source temperatures. And then I think this kind of product might be not efficient because if the temperature, for single effect you need a heating source about 85 degrees centigrade. And the double effect about 140 degrees centigrade. But if it's go between, say, 120 degrees centigrade, it could be already using single effect to operate, but efficiency is very low. So in this case, we invented this kind of new concept, so-called one-point-N effect. And actually, to compare with normal absorption chillers, I added the high temperature absorber and the low with a second generator. That's using the absorption heat to make a generation. So this is actually the absorber generate. This is we added just 2 units, heat exchangers inside this system. And then this system could be capable of single effect when the temperature is about below 90 degrees centigrade. And when the temperature is above 140 degrees, double effect. And if it's will be changed, it could be changed the efficiency. So this is our new design and already tested also in this year. And I expect that this kind of machine could be commercialized for widely application for solar cooling. In this case, this could meet the requirement according to the temperature levels. Different temperature levels, we get different efficiency. And also we developed ammonia water absorption refrigerator. So this is very specific design. Actually, we have two units. One is use desorption side to use the waste heat from exhaust gas from internal combustion engine for the generation of ammonia water to get the desorption of ammonia. And we have the user side. It's a kind of condenser and evaporator. You output the cooling to the user side. So this would be combined just by piping. And so in this case, this is the user side and this is the generation side. But for this, normally for ammonia water system, you need liquefaction column because ammonia just dissolved into water. But if you generate, you also bring some moisture, some vapor. So ammonia is not 100% ammonia. It could be 95%. In this case, some water will come into as a refrigerant. So if it's a slaughtering process to temperature below 0 degrees, it will be ice float. So in this case, we need a liquefaction column. And ammonia needed to be purified in this case. But during the process for liquefaction, you generate some heat. And this heat could be used in the process. So in this case, we made the use of liquefaction heat. And in this case, we tried to improve the COP of the refrigeration. So what's the COP? Normally we developed about a 40 kilowatt refrigeration unit and generation temperature 160 degrees centigrade minus evaporation temperature minus 30 degrees. And you get a COP 0.4 to 0.5. That's very high for refrigeration purpose. So this is our design machine, and also the design of the machine, because we consider originally this is used for the waste heat driven absorption refrigerator ice maker for fishing boat. So this will be put on the boat for fishing. In this case, the fishing boat needn't bring any ice when they go outside for 2 weeks or 1 month, something like that. So in this case, this kind of machine, if it's installed on the boat, it should have the function of anti-swelling of the boat. So in this case, we had a very specific design to use heat exchangers, but we use capillary tube heat exchangers. The inner diameter, that's about 1.7 millimeter. That's a stainless steel tube. But for the heat exchanger, it's more than 1,000 meters. So it's very densely with the heat transfer surface. So already before, we do not have the data, but we made the design and then we succeeded for this. And also recently we are doing for the desiccant materials used for heat pump. So there are a variety of uses of desiccant cooling. The first, if we see the traditional heat pump during the summertimes, we get the evaporation temperature should be much lower than the dew point. The reason is that you need to get the evaporator, the room side. So surface temperature should be lower than the dew point. And due to the temperature difference of heat exchangers, normally the evaporation temperature will be about 5 degrees to 7 degrees centigrade. And then you get the indoor unit, the surface somehow between below 12 degrees centigrade, and it's less than the dew point. So this is used for dehumidification. So this process, that means you need a very low evaporation temperature. So this efficiency is not good if it's very low. But for air conditioning, inside room, we need 26 degrees centigrade. So in this case, it would be advisable whether for normal vapor compilation system, you could increase the evaporation temperature from 5 degrees centigrade to 15 degrees centigrade. That means, in this case, dehumidification will not be possible, but efficiency will be very high in this case. So in this case, we need dehumidification by desiccant materials. Now, there are several ways to use desiccant materials if the air is dehumidified. Maybe one stage or maybe two stages. To very dry air, the temperature will be increased due to adsorption. So then you combine together, you get the cooling down, and then by evaporative cooling. This is normal. Use it for solid desiccant cooling. So no other needed. But you need deep dehumidification. In this case, you need a desiccant rotor or desiccant liquid. You need the solar heating to make the generation. So solar heating temperature should be higher than this temperature. Yeah. So if it's 80 degrees, then you need the solar heating 120 degrees centigrade. In this case, it's not so reasonable. And then some people consider to use it on heat pump. And we have a desiccant rotor. It's dehumidified, not very dry. It's a little bit dry. And so temperature not very high, so then cooling down by the evaporate. And then you get the reasonable temperature. So this is, in this case, it's a kind of desiccant rotor combined together with normal vapor compilation system. It's called independent temperature and the humidity control. Humidity is handled by a desiccant rotor, for example. Temperature is handled by the vapor compilation system. But you need the regeneration for the desiccant materials. In this case, for example, if it's 60 or 70 degrees centigrade, and then possibly you use solar energy, 100 degrees centigrade for the regeneration. So this, you still need solar energy or electrical heating for the regeneration. Actually, this may cause the system to be a little bit complicated and investment to be high. So in this case, we could see from the figure, if this is onto your temperature and humidity, if we want to treat directly to the comfortable region, why we need to go this way or go that way? Why we cannot go directly? So this is actually a kind of near heat pump. What we are doing. So we just put, for example, the humidification in summer. We have evaporator, we have condenser. So this is a normal vapor compilation system. And we put adsorbent desiccant materials on the surface of the evaporator, on the surface of the condenser. So during the evaporation, if we have 15 degrees centigrade for the cooling, so you have high efficiency. But if the air comes due to the desiccant material, air becomes dry. And also, the adsorption heat will be taken away by the evaporation. So because you increased the cooling capacity, so you consume some cooling capacity for the humidification. In this case, you get comfortable air directly and put it in the room. But you need, try to, for the how to make regeneration of the desiccant materials towards in the condenser. If we have 15 degrees evaporating temperature, condensing temperature could be somehow between 45 to 50 degrees centigrade. Originally, this condensing heat rejected to the ambient air. And now, this condensing heat could be partly used for the regeneration of desiccant materials. If the desiccant material, for example, is condenser, originally, if the condenser was evaporated, so after it's become wet, absorb a lot of moisture air, and then it needs to be regenerated. So in this case, what we could do is just to have evaporator and a condenser change the phase. Maybe every 5 minutes, change the phase, operated by the four-way valve. In this case, you simply have a normal vapor compression system. But the two heat exchangers that's coated with the desiccant materials. So evaporate and condenser could be switchable. So this is for the summer dehumidification. And in this case, you get a COP of our vapor compression system higher than 5.2 or even 5.5. So this is a very high efficiency. And also you control temperature and also humidity. So this could be a new concept. Also we are going just on the way of research and development. And also in the winter time, we could use the desiccant material to take some moisture from the air outside and then inject it, import to the room side. When the room side is heated, you added some moisture to get increase the humidity in the winter time. So this you get more comfortable. That's a new. And currently, Japanese company Daikin, they developed so-called Desica for the independent humidity control. So they use VRV for cooling, Desica for dehumidification. And now I put the concept. Not only that, we could go together. In this case, to make the system more compact and more efficient. So above that is just to let the audience know what I'm doing in Shanghai, Jiao. So with the sorption technologies going to be used for heating, cooling, and also a variety of dehumidifications. So in this case, adsorbent is the key for my research. And now then we turn for today's lecture, so-called thermal energy storage. So thermal energy storage, everyone knows. But whether the industrial waste heat or geothermal heat or transportation engines dissipated heat or solar energy could be stored, could be stored. And then we could use it when it needed. So this is the topic for thermal energy storage. And everyone you know electric storage is the battery. You could charge the battery and could release for discharge for the uses. And actually we do need thermal battery. The thermal battery is that you recharge the heat, and when you want to use, you export at certain degrees you need it, and at a certain power you require it. So this is actually the concept for thermal energy storage. And we could clarify the thermal energy storage in 3 categories. One is sensible heat storage. So everyone knows the hot water tank. It's a sensible thermal storage. Or we use some soil. We use rock, for example, heated by sunshine, by solar energy, but it could be used for heating in the winter, for example. And there is also so-called latent heat storage to use PCM, phase change materials. Whether it's a kind of solid to liquid phase, or solid to solid phase, or liquid gas phase. These are phase changes. Phase changes, we have the latent heat. The latent heat is usually far bigger than the sensible heat. So this area already there are a lot of researchers. And today our topic will be thermochemical heat storage. And it's could be used thermochemical reactions or sorption process. For example, physical adsorption or chemical adsorption, or use some chemical materials with some chemical reactions. This reaction rate could be used as a thermal storage. So this, in this case, we need to know why we need this. The reason is simple, because the thermal storage density for sensible heat is very low. Latent heat somehow better, 3 times or 5 times, for example. For this, you get 10 times or 30 times, and the density increased. So in this case, it's possible to make thermal energy storage system with compact sizes. So here we could see from the International Energy Agency, and they have a report just last year. To say for the sensible heat storage, it's very major for the market. For hot water tank, it's very major. There are some still research, maybe 5%, but mostly that's in commercial uses. But for the large water tanks, maybe still there are a lot of uses. But some demonstrated in engineering. So this is for the sensible heat, and the sensible heat need the simple thermal insulation, for example. But it's very simple to deal with. And then comes to the PCM. And the PCM is widely accepted for the cold storage with ice, for example. We call it ice storage for cooling, for refrigeration, air conditioning. So this is widely accepted and also already used for commercial building for air conditioning. And it could be also, recently there are a lot of research for ice slab. Maybe the temperature, this kind of ice slab, the temperature could be about 7 degrees or 10 degrees centigrade. But energy density of ice slab is much higher than normal chilled water. So there are more and more research, but now the market is available, and still there are some researchers. And also they have some passive cooling for buildings. You use some PCM materials embedded into capsules or integrated into some building materials. So this could be used to absorb solar energy. So during the day, and then change the phase to liquid. But in the evening, in the night, the liquid will release heat and it becomes solidified. In this case, we will go for the wind heating. And also, there are some research for high temperature PCM. This could be used, for example, for solar power station. You need 400 degrees centigrade or even more. So you use some molten salt, for example. That's a PCM. So this is in the phases of R&D, not in the commercial uses. And then we say something about the sorption thermal storage, for absorption thermal energy storage. So already 5% in use, but mostly for research and absorption, the same, and also other chemical reaction. That means this new topic, that's a research hot point. Currently also for International Energy Agency. So they have for energy thermal storage, so topical, the working team. So a lot of people are doing. So this normally is still with high cost and complexity, and it has relations clearly with the materials. That's a key for the chemical thermal storage or sorption thermal storage. And these figures give you why we have sorption thermal energy storage. Because if we evaluate for storing thermal energy storage for water, for example, if we had a delta T 70 degrees, that means it's 20 degrees to 90 degrees. So this thermal storage is 10. So if we get some calculation for 1 cubic meters of chemical reactions, you need about 34 cubic meters for hot water with a temperature lifted of about 70 degrees centigrade. And you could have possibly sorption thermal storage, maybe physical absorption for 10 cubic meters, and a latent heat you need about 20. So in this case, so this is very major. And then latent heat already commercialized. And now sorption and reaction seems to be very, very important and with high thermal energy storage density. And we could combine together with a chemical reaction or sorption because it's actually all related with some adsorption or chemical reactions. We unify this as a sorption thermal storage. In this case, you could see that this is the temperature degrees and this is the power densities. So normally the sensible heat is here and then the PCM and then sorption and then chemical reaction. So in this case we need normally for the temperature somehow between 80 degrees to even higher, better we use sorption, thermal and storage. So now I say a little bit for the basic concept. So this is the basic concept if we have sorption materials. If you heat it, and then the working liquid, working substances. For example, if you use zeolite on water, if it's heated, and then water will be dissolved, condensed in the condenser, and then accumulate in the receiver. So this is the process. The thermal heat changes to chemical potential energy actually. So in this process, if we start from here and if it's heated and then to this point, then generation stop. And then that is over the bed maybe cooling down. It could be kept for several days or several months. Energy always there. If there is no leakage to the outside. So if the bed comes down to the room temperature, for example, and then if you want to use the energy, you just combine together this reactor with the evaporator. Open the valve, and this, because this reactor it already has a very low pressure when it's generated and cooling down. In this case, if it's connected, you get the evaporation of the liquid here, and this, in this case, you also put cooling. So this cooling could be used. By the way, for the reactor, you need, due to the sorption process, you have an adsorption heat, and this heat should be released. So this could be used for the output or heating. So in this case, if you design the system where it's a kind of one stone with two birds, actually. So you have the one stone, just the sorption process. You get the cooling and you get heating. So, but you need the design if the cooling temperature is customarily needed, or heating temperature also needed. So in this case, the efficiency is very, very high. So this is actually the concept. And this could be zeolite water, or calcium chloride ammonia, or other zart with ammonia, for example. So this is actually a kind of process related with this heating or cooling, desorption or absorption, for example. And here, in this case, for the sorption thermal energy storage, we could have liquid absorption, solid adsorption, or sorption reactions, chemical reactions. Or we could have combined some sorption process with physical adsorption or chemical adsorption into some composite materials. We have composite, mixed absorption. So in this case, we have a lot of options for the selection. It's with a high power density, and in this case, according to the demand of the users, we need to make options for the selection. And this table just shows the difference of sorption and sorption thermal energy storage. For the sorption refrigeration, the key evaluation parameters is the COP. So you import the heat, how much percent could be transferred to cooling? The COP is the cooling power divided by heating power actually. And also the power density, output power, and also the cost. So this is a critical key point for sorption refrigeration. But for the sorption thermal energy storage, we need the high thermal energy storage density. So that's different. And we need to consider storage efficiency. If you put 10 kilowatt hour in, and how many kilowatt hour could be output? So this is the efficiency for the thermal energy storage. And we also need to consider the power density and also cost. But for the refrigeration, you need to consider cycle time as short as possible to make the system compact. But for this cycle could be 1 day, and 1 month, or 1 year, depending you need it. So this storage could be for a long time. And the system scale, normally this is for cooling, could be several kilowatt to several tens kilowatt or 100 kilowatt, the cooling power. But for this, you have so-called kilowatt hour storage capacity, and or there's a 10 kilowatt hour or 1,000 kilowatt thermal energy storage. And for the materials, it's totally different. You see, for this material, for sorption refrigeration, we need low desorption temperature. In this case, it's good for the usage of waste heat. We need this material to have low heat absorption. We need high sorption changes, concentration changes, but the heat absorption should be as small as possible. And we need high heat evaporation, so this is for the refrigerant. But for this sorption, thermal energy storage, we should have reasonable charging temperature. This depending the selection of the output heat and what kind of temperature. And but we need a high heat absorption. So this is different. Yeah, this is lower. This is need high. So the development for the state for this and the sorption refrigeration machines now is already commercialized major. But for this one, maybe in the next 5 years or 10 years, I think this will be a challenging field, and more and more people are involved for thermal energy storage for research. So there are 2 examples. We show short-term thermal energy storage. For example, could be 10 hours something. For example, this shows the charging was charging in the night, in the winter time, charging the night. For a club, we use the heat from the network and to generate zero light water and to make the zero light result during the night. But during the night, but it is used for the office building, for example. During the day, we could use absorption heat. And this heat could be output to the building for heating. So this is actually one constellation. Thermal energy storage used only after several hours in 1 day, or just a half day, for example. And another example is for the seasonal thermal energy storage. So we could have, for example, your solar energy, and during the summertime you get the regeneration. For example, using my water, you get the water dissolved. And then at last you get the strong solution of water, and then water accumulate in the condenser and into the water tank. So this is during the summertime. But during winter time, you just elate a strong liquid of lithium bromide to absorb water. And in this case, it's connected to the ground source. So sometimes the condensing heat put it in the ground source. In the winter time, the ground source is used to heat evaporate. In this case, you get some absorption heat released at a high temperature, more than 30 degrees centigrade to heating the room. So this is for the transient thermal energy storage. In this case, you could see that normally this kind of heat could be kept for a long time. Just no thermal insulation is needed because you change the thermal energy to chemical reaction or chemical potentials. So in this case, you just leave it there. If you want to use, you just open the valve for the connections. And the material selection will be the criteria. So there are a lot of options. So I think for the energy institutes and also material people, they should collaborate together in this case. We need high energy density for the storage. Or normally we could have how many kilojoule per kilogram. For example, for PCM, normally the 1 kilogram phase change material, you get a heating for thermal storage, maybe 150 kilojoule or 200 kilojoule. But for the chemical reactions, it could be 1 solid or 2 solid. But this is what the high density. Or we could evaluate according to the volume. How many, the 1 cubic meter, how many kilowatt hour could we store? So this is an evaluation for the materials. And also we need appropriate heat and mass transfer to ensure good charging or recharging or release. In this case, we need a design output of power. For design output of power, you say we have 20 kilowatt hour, I need 2 kilowatt hour or 5 kilowatt hour. So this could be easily controlled. But if you have more flexible output hour, output power, you need a very, very good heat transfer with the thermal fluid. So this heat exchanger will be very, very critical. So not heat exchanger itself, but the thermal connectivity of the thermal and storage materials is very critical. And also we need it to be easily handled. So, and also low cost. And also the material should be stable for long term. And also with some mechanical stability. So this is a requirement actually for materials. And today I say something about the thermal energy storage based on absorption. This just shows lithium bromide water or lithium chloride water. They are used for absorption. So lithium bromide water already commercialized for cooling. So in this case, what we need to consider is several working fluid, lithium bromide water, lithium chloride water, or calcium chloride, or ammonia water, or that's sodium hydride water, for example. So these are the working pairs used. And but it's mostly very important is some crystallization temperature. So for the liquid, you do not want to change it to the crystal. So in this case, for different materials, they have different temperature. For example, lithium bromide water, it may have about 100 degrees centigrade. So you control the temperature and the pressure into a suitable level. You could always have the liquid. So you make the liquid water concentration changes. You store the energy actually. So this is one example to use the absorption and use sodium hydride water and a heat pump for long-term thermal energy storage. So actually you could have charging the heat and you get a desorption and the condensation of water. So the weak solution will turn to the strong solution. When you want to use, you just put a strong solution there and then to try to get the absorption, to get evaporation here. And then the liquid turn to the weak solution. But in this absorption process, you output heating. So this is going to be concept could be demonstrated and used for the long term. So this could be, we need about 150 degrees to generate this material. And the example shows 3 kW heat input and output on 600 watt, 6 watt. This is a demonstration unit already done, but it's, you could see that it's very small, and the heating output is also very, very limited. And then in France, there are some researchers for this. You can see them. Some started with lithium bromide water, and they are building the system, and the system is not in good order for their testing, actually. And another good example, this is a successful example in Tsinghua University, and there is a CCHP, combined cooling heating and power system, and then the heat from the engine, they could recover for the thermal storage to use lithium bromide water. Actually, in this case, is one tank with lithium bromide solution and another tank with water. And in this case, they get nearly, for chilled water output for energy storage, they get 1 cubic meter for 31 kWh. But for 60 degrees hot water output, using absorption heat release, that's about 42 kWh per cubic meters. So this system already integrated into the CCHP system with flexibility for thermal energy storage. And now I say something more. There's a publication of my student in energy, and we call this evaluation of 3-phase thermal energy storage sorption cycle. We use the concept of lithium chloride. So lithium chloride water is a kind of solution. So this kind of liquid solution could be heated. If it's heated, you get dissolption of water, and then concentration of lithium chloride will be more strong. And to the point, you put all the water away, then it becomes a crystallization. But this crystallization actually contains some water. So you could get the water away, actually, so get the water away. And then, if you heat it again, some water could, in the crystallization, in the crystal, could be separated. So in this case, you have first step only the concentration changes of water. The second step, you have the phase change, PCM, like PCM, from solution to solid. And then the solid could be even make changes when you heat it, and then some part of water will be broken. So in this case, you have 3 phases. And this 3 phase changes what's the energy density. So this, you could see that if we evaluate the sorption thermal energy storage density, and this could be very high. This is in kilowatt hour per cubic meters. If it's in kilojoule per kilogram, it's nearly about 2,000. So this could be, if you use the data to compare with normal PCM, it's pretty high. So the storage density, if we're here, this is we use lithium chloride water, calcium chloride water, or lithium bromide water for completions. You'll see for the cold storage, it's a very high with that for the storage density, actually. And or for heat storage. So to compare with calcium chloride, lithium bromide, it seems that the lithium chloride with the 3 phase changes is very effective. So this is material actually now we are in use to develop whether it's possible to have 300 hot water with 90 degrees centigrade, reduced to less than 150 liters. So this is the first task we agreed with the company in Japan. So we try to develop this into commercial modules actually. And there is another example already used for solar air conditioning. So they have just developed here the reactors. This reactor actually using lithium chloride, it could be turned to crystal. And this crystal, so it could have some function on the absorption of water. So it could be have, so start from absorption of lithium chloride on water. And then after it absorbs so much, it will be changed into liquid. And then the liquid could still continue for absorption. So in these cases, it could combine together. This is the only product from the company so-called Klimatware in Europe. That's sponsored by that's IEA, Solar Heating and Cooling Task 32. Just 2 days ago, I got an email from this company. They want to show to people. They have big systems for solar heating and cooling, but with energy storage inside. So they already use this concept and try to penetrate in the market. Personally, I think this could be a very good solution for solar cooling used for residential. It's very simple, actually. So during the day, you get the illumination, but in the night, for the cooling at home. So then I want to say something, thermal energy storage based on absorption. So for the absorption, there are a lot of materials. So zeolite water, silicate water, and currently there are some other materials, maybe, for example, MOF. So MOF is specifically designed for the absorption of vapor. The surface area, specific surface area could be 3,000 or 4,000 meters per gram. The only problem is that in the market, in the market we could buy several grams. It's impossible at the moment to buy several kilograms, and very expensive. So this is just less than the material people they are doing. If they could be commercialized, this could be introduced for absorption, thermal energy storage with high density actually. There are already 2 or 3 papers to make the evaluation of this. And currently Professor Zaha in Kyushu University is also doing the research. And we discussed with our chemical or material people. The problem is that now we could get 1 gram for testing only, so not for the engineering uses. So this shows that there are a variety of selections. For the selection of adsorbent we need, so the big changes of concentrations in a fixed temperature level, but we also need for the adsorption heat as high as possible. So this multiple together will be the figure of model that for the option of the thermal and storage solvents actually. And at the moment, I think there are some research, for example, Mitsubishi FAMG02. Now they are developing some very modified zeolite. Now it's commercialized, still very expensive. And we think it's much better than normal silicate water. So we do hope that Mitsubishi material, the Mitsubishi chemical, that could sell more in the market. At the moment, it's just for the demonstration test, and Mitsubishi also they built absorption chillers with this kind of material. And this is another example to use silicate water for the thermal energy storage. Normally, silicate water is not the commodity because For this, the adsorption rate is not so high. And also the changes on concentration is a little bit limited. But this is an example that have adsorption rate and the water tank. So if you heat it, you get the desorption, condenser, and liquid is accumulated there. If you want to release heat, you just open the valve and to get the evaporation here, and so by the adsorption heat could be released. But this is an example that's from some colleagues saying, with the balance that they reported in the year 2008. I think that the system is not well designed. Actually, they use water as a vapor. So you could see the experiment. For the water, you need a bigger diameter of tubes. So if you use ammonia, it will be okay. So they developed this system. Actually, there's some test, but this test should have some capability. So this is a 13 kWh system, and with some efficiency that to compare with normal water, that's about 71% for the charge and recharge ratio actually. And this example was from Shanghai Jiao Tong, and in the year 2003, very early, and I remember very well because that's the year of SARS in China. And we have a task actually in collaboration with railway companies to develop for the internal combustion engine waste heat could be used to generate adsorption cooling with zero light water. So we developed a system and demonstrated there and verified it's possible for the locomotive cabin for the cooling to 26 degrees centigrade. So in this case, we have only one single adsorber, and it's driven by the exhaust gases. And then cooling down, when it's moving, cooling down by the air. And then it has the adsorption capacity, you get the evaporation of the water in the tank. And if you have some big volume, you store some refrigeration effect inside of the tank. And also you output to the cabin cooling. So when you have some storage tank for the thermal storage in this case. So during the generation or desorption phase, we could use the cooling effect stored here for output. So during the adsorption, we have enough cooling. So in this case, it could be stored in this cold water tank. And another example, I already showed that in Germany, they are using the charging in the night by the network heating, and for adsorption, you get desorption. And during the day, they need the room for heating in the winter, and then using the adsorption heat to heat the room. That's I think this project was in Munich, actually. And I observed possibly this is a very good example for already used the sorption thermal storage for the real engineering applications. And for the commercial uses, now this kind of thermal energy storage already used in the market for the washers drying, actually for the dishwashers drying. And here you see the normal conventional dishwashers. So you use the electric heat, and then just by spraying and then heated the dishes. And then you need the heating to dry. So the heat all released to outside. So this is a conventional one. But now the dishwashers with adsorption drying is commercialized. This is not only for dishwashers, also for the residential washers or for clothes. Originally, people use heat pump, but this is another option where they use desiccant adsorption materials. So when it's heated, you spray the hot water, or some heated air goes for the regeneration of zero light or silicon air. And then when it's finished, you just circulate the air, and then by the adsorption, this chemical, the air turns to be dry. So this is actually commercial product to use zero light on the adsorption of water to make a dish washer to be more efficient. The energy saving could be more than 24%. And also people use this thermal energy storage, sorption heat storage, connected with building by the solar heating. By the solar heating, they use solar heating for the regeneration of the sorption materials. And possibly it could be seasonal or daily for the applications. So for the usage, you just connect this and then release the sorption heat. So this could be closed system or could be open system. But open system seems to be more easy for the usage. During the day, you make regeneration. You take the moisture all inside away. But in the night, if you want to heat it, you just pump the air, moisture air comes in, and then it releases heat or adsorption. This could be used for heating for house. So 1 cubic meter, you get about 130 kilowatt hour. So that's a very big power density in this case. And the most challenging project investment was from MIT. So they announced for the electric vehicles, because electric vehicles, they use battery. And if they use battery, now the battery may be used for 140 or 160 kilometers. But if you need to operate for heating or cooling, you get nearly 30% down. So in this case, there are two ways. One is to have more battery used. The second way is, whether it's possible, you do not use battery for heating or cooling. In this case, MIT, they are suggested to have a thermal battery. Actually, to use adsorption, they use zero light, adsorption of water. So by this process, you output cooling or output adsorbent, you could output heating. And normally, the design they need about power output about 2.5 kilowatt for automotive vehicle. And then the total power store, energy store for cooling, 2.5 kilowatt hour. So normally they design, if we have cooling power, 2.5 kilowatt, maybe you drive for 1 hour. Or heating, 4.5 kilowatt hour. And this was designed only with 35 kilogram and only 30 liters, very small compared. And they evaporate around at the cooling for 0 to 5 degrees centigrade. But for the regeneration of zero light, you need about 200 degrees centigrade. And then I discussed with them how to make a regeneration. They said regeneration is they're using electric heating. So when the car is parking there, you plug the electricity. So for the battery, also for the regeneration of this thermal battery, adsorption rate actually. So this, they promised that Ford, Tesla Ford Focus start at this year, March. Now I'm waiting for the report, for the results. It's not so easy, but because MIT people, they had no experience before with the adsorption rate. And also this system using vacuum, actually you need a very good vacuum tightness. Or if it's in use, for the start point, there are some inert gases. If you do not treat it well, the system cannot work. So, because I think for these guys, originally they do not have the experience. I think the concept is good. So we do hope they could get good results by zero light water. They expect for the future to use more of water. It will be more compact. So if this could be used, then it will push the market for electric vehicle very, very quickly. And now for the automotive industries, so GM and Ford, all they are paying a lot of attention for this. But I think it's not easy, and if this could be generated, it will be big push for the thermal energy storage using sorption materials. And then I will say something, sorption reactions. That means with a chemical process. And with a chemical process, you get a much higher power density. And normally, for example, if we use some salt with chemical reaction of ammonia. So in this case, the energy density could be valuable, nearly to highest could be 2,000 kilojoule per kilogram. Mostly more than 1,000. So many materials could be selected. We need to select cheap materials. Actually, this paper was published in I²CNER journal by my research group. And then we selected some example, maybe ammonium chloride and sodium bromide could be very good options. And the working equilibrium temperature is this temperature is very good for the output heating in winters. Or this is good for the hot water tank, actually. And then there are some other manganese chloride, or even nickel chloride. So different temperatures, equilibrium temperature could be considered. So just on the demand, what kind of temperature is required, and then we make selections. So for the chemical action, you have a lot of options. So here, this figure I just show you, it's still even possible for energy upgrade. For example, we could say, if you give me the energy low temperature grade at about 90 degrees centigrade, with this kind of chemical action, we could upgrade to 170 degrees centigrade. So with heat, will become to usable heat for the process. So 130 degrees could be lifted to 280 degrees centigrade. So this is depending what kind of chemical reaction substance is used. For example, in this case, we need two adsorbents. For example, manganese chloride as a primary high temperature adsorbent, and then calcium chloride as a low temperature adsorbent. So if we have two adsorbent beds, and if, for example, we generate with 87 degrees centigrade at this temperature, and then you get release of ammonia to another secondary reactor. So ammonia will be dissolved and then absorbed in this reactor. So you heat it, you get ammonia dissolved, and this ammonia comes here. And when it comes here, so this secondary reactor, and then we generate the second reactor at the same temperature, also 87 degrees centigrade. And then you get another release. So, and this released ammonia could be condensed in the condenser. So this is a satellite line. So after this satellite line, and then we let this adsorber connected with our evaporator. But the evaporator temperature is not for cooling. We just use ambient temperature, or could use this temperature. So if we use ambient temperature, it's higher than this temperature, and then at this satellite pressure, you get the release of ammonia, and then this comes here and it's absorbed. During the process, you release heat, so the temperature will be here. So in this case, you increase the temperature from 80 degrees, 87 degrees to about 170 degrees. And by control of this pressure, you could have controlled output of fixed temperature, actually. So this is for the upgrade of the waste heat. So this is a very good concept. for the applications. And also we could consider for the seasonal thermal energy storage. For example, if we have 2 gate and we consider if it's regenerated but it didn't winter time, and this evaporation temperature from the ambient is very low, and we could use this adsorption heat to heat another evaporator, and then you get release of heating. So this is actually what we have done, and we found that this kind of function could be used for also for seasonal thermal energy storage to increase the release, the temperature of heat release actually. And then we could see one example from France. And this example we just use also that there's a barium chloride ammonia. So they use about 80 degrees centigrade solar collector during the day to make the regeneration. And in the evening, in the night, they use this adsorption of ammonia again, and then to output the cooling to make ice. So this they already tested, and they could get 40 degrees cooling output for air conditioning. And then we have more for some chemical reactions. So it is also, we published paper in also the applied energy for use the resorption process. And there are also other chemical reactions, so-called hydration reactions. You have solid, and we take in the moisture of water, you get a little bit something dissolved. And then you dissolve more if humidity is continued for sorption, and then add a lot to the solution. So this process could be also used. So in this case, there are a variety of that could be used for this so-called deliquescence process. And recently now there are some constellations whether it's possible to have physical resorption, for example, silica gel or zero light structure. It has the micropores. And then we added some lithium chloride to the liquid comes into the micropores. In this case, you get a combination of adsorption and also absorption. So it's a kind of physical absorption and chemical absorption. So in this case, you get much higher density for the energy storage. So this was proposed by Aristotle in Russia. And there are more, and for the workers hydro reactions with manganese sulfur oxide, and also mixture manganese sulfur oxide zeolite to be heated, adsorption on moisture on water actually. So the energy density could be about 1 kilogram, get about 650 kilojoule, for example. And there are more researches for manganese chloride water, and yeah, you could see there are different the water content for the crystal actually. So you just buy this kind of fish changes. It could be changed several times. So this all the phase change heat could be used. And there are something more. I think I will not come into very details. And also we have sodium sulfur actually. And some French team developed a system and tested. This is adsorption rate. Put this kind of material into, and then for the absorption of water. And they have the efficiency for thermal storage about 56%. They use 3 kilogram result, and they get about 2.0 kilowatt hour for thermal energy storage. And the French team, they will continue to do with different samples, yeah, by a humidification process, and then with the absorption of moisture, and to see the energy storage density. And they even developed a system, but the system is not well designed. I think in the moment, in the world, there are a lot of demonstration test units, but the structure of heat exchangers is not well considered. So they just develop a system and test it, and then they found that it's not efficient. Then the project is stopped. So this is actually the program. So normally for the research, we need to continually make the modification. And the best way is that for the design, first stage you have very good design of the whole heat exchangers. And this is another one for calcium chloride, silicon gel on water in South China University for Science and Technology, open system. And currently for the lithium chloride silicon gel on the moisture absorption of water, so this is in Shanghai, we have a similar so-called local thermal here. We can also have, we use this, and we test it, and then we find that this system, we use a composite adsorbent. So silicon gel, lithium chloride, and lithium chloride have a 40%. We tested, so in this case you have bigger power density for heat storage. And in Japan, Hokkaido University, they use honeycomb filters, composite materials for open sorption systems. That's open for the moisture absorption. So they tested that, and 1 cubic meters of this thermal storage, you get about 76 kWh for heating. So this is just what I said, and you could see it's not nature. This is the beginning point for the sorption thermal energy storage. So there are actually for different output temperature, there are a variety of selections. So for the selection of materials, so what we have, we collect a lot of data and put it here. And then you see there are a lot of options. For the selection, you need a very good adsorbent. And chemical reactions, you need this material to be cheap and stable in working. And so there are a lot of selection. You need a bigger absorption rate for the thermal energy storage. And we proposed some bromizing aluminum solvent, for example, barium chloride for 56 degrees centigrade, calcium chloride nearly 100, manganese chloride 150, and iron chloride for nearly 190, and nickel chloride for 260 degrees centigrade. So this could be considered, and this is actually their power density. So this is the option that, based upon our research, we combine these kind of materials. And also, for the water, this is for ammonia, but this is for water. We call it zeolite. And the lithium chloride, and that's sodium sulfur, or sodium bromide, or manganese chloride water, or manganese sulfur oxide. So at a different temperature also. So based upon, and then I concluded that in the world there are various research groups, and what's their achievement already had. And I would say the most work are focused on the material level, and the practical thermal energy storage devices are still limited. Even in this prototype, few satisfactory experimental results could be found. So there are big gaps for us to fill and to achieve for the research. Through our research, actually, we think that the heat and mass transfer issue is very, very important, because this force chemical reaction solvent, you need to charge it, the heat easily output, release heat very easily. So you need very good thermal conductivity. But for adsorbent, normally conductivity is only 0.2 watt per meter per degree centigrade. So when it's possible to increase to 20 or 30. So I will show you that what we have done. And also, to bring the sorption and the technology in the market, we need the intensive study for the fields in the evaluation, advanced materials, and development for the efficient, compact prototypes. And we have the options to select an open cycle or a closed cycle. Open cycle is very good for heating to the room, so just by vapor to be the refrigerant or for working substance. And normally open cycle you get a very satisfied power density. But if for closed cycle you need a very complicated heat exchange design. And then at the moment we also need to consider the cost. The zero light, lithium chloride, lithium bromide, or different materials. So we need to get the unit price down. So this is per 1,000 kilogram, how many dollars it cost. And also, we could, if we evaluate the cost per storage 1,000 kilowatt hour, and then we find calcium chloride water or manganese chloride water or something, or not, or that's sodium sulfur, for example. So this is just a bit for the cost. And the control output temperature and power is very important. Because for this you need the control temperature and control power. So heat transfer design is very, very critical. And also we need to consider the heat capacity wasted for the inert material, steel for example. This material do not consume a lot of heat, but release very less. So in this case, we need to consider that the heat exchanger should be the mass and the heat capacity should be small, but has good thermal conduction. And the cycle stability for the sorption material should be repeated 1,000 times or 10,000 times. So this is very critical. And we need, for the calculation, for the energy storage density, not only kilojoule per kilogram, that's for the material, but for the unit, it's kilowatt hour divided by the cubic meters of the system. So you need, at last, the whole system to be small. And also, for the solution, for example, liquid or gas, you need the 3 separate storage tank. So this will be considered. Or crystallization steel. For this, you need a lot of things to study. Also, for this liquid desiccant materials, pollution is very critical. And recently in Shanghai, Jiao, we developed a kind of so-called consolidated expanded natural graphite that's treated with a sulfur. And this, we could get a thermal conductivity as high as 330 watt per meter degree centigrade. So when I say this, Professor Xing he never, because we think for the nanotubers, it could have a value very high. But if it's integrated into blocks, normally the high thermal conductivity losses. But for the expanded graphite, we tested several times. So not only tested in Shanghai, but also in UK. And then we find it's really good. And then we tried this combined together with calcium chloride or activated carbon into the bricks. In this case, we get about 30. So this is for the real adsorbent weight, about 34 watt per meter degree centigrade. So to compare with normal adsorbent 0.2, so it's a big increase. So in this case, you will save a lot of heat exchange surface. And the heat exchange could be more simple. And the system will be more reliable and compact. If you have big heat exchangers, you occupy big space. And also for the solid gas systems, you need to control whether you have some carryover of some liquid solutions. So this is very critical for specifically for the composite adsorbent materials. And now in Shanghai, we are doing for the latent thermal storage. So this is the example what we have done for the potassium nitride with expanded graphite. And so with our technology to get a thermal conductivity, this is about 15 watt per meter degrees. And then develop a PCM, this is one example. for 330 degrees output used for solar energy. Another way is for chemical reaction. We use calcium chloride and expanded graphite ammonia. And normally the discharging temperature is about 150 to 170 degrees centigrade. So this is already finished, and then now it's prepared for testing. And also, what I already mentioned, because Shanghai, Jiao, we made it commercialized of this kind of air source heat pump water heating in the year 2003. And then we get the requirement whether this tank could be reduced. Actually, this tank normally family that's only 150 liters. For in Japanese market for CO2, that's 300 liters. The difference we take short, Japanese take off full, that's different. So in this case, whether we could reduce to 50 or 80 liters, then it will not occupy the space on the ground space. So in this case, we are considering whether it's possible to use three-phase sorption. So this is our next work on the way. I hope that next year I could give the report for the progress, and also we'll get the contract from Japanese Mitsubishi Electric for this kind of collaborations. So thank you. I think this is actually what something we have done based upon sorption refrigeration, and we want to push sorption, thermal, and storage. Shanghai Jiao already started a little bit. In the world, there are already a lot of research achievements, but at the moment, it seems that it's not major. We don't need in the market to have some this kind of sorption, thermal energy storage, or so-called thermal battery. Thermal battery should be at the discharge temperature, at a fixed temperature, and at a requireable, controllable output heating power. So this is actually the goal for the thermal battery. And I expect in the next 5 to 10 years, so this will be expanded for research and commercialization. So thank you all. So this is my laboratory, so-called Green Energy Laboratory in Shanghai Jiao University, and in the future, you are welcome to visit my laboratory. Thank you very much.